Hello students, this is Professor Chalai, and in this video we're going to start to look more in detail about the quantum mechanical model of the atom, and specifically we're going to start looking at quantum numbers. As always, you can follow along with our Chapter 6 workbook. Let's get started. So far we talked about how the electron moves as a wave when it's inside of an atom, and this explains, for example, line spectrum. Let's go into a little bit more detail about what we can learn from describing electrons as waves. And as always, we're going to start with this very simple model of a wave in some box, right? So if I tell you this was some box, and I wanted you to find all of the waves that could fit in that box, you might come up with some solutions like this. So the simplest one would be just one little wave like that. And then you get more complex and even more complex and even more complex. But you will get a whole bunch of waves that can fit in this box, not just one wave that can potentially fit in the box. All that we need to make sure is that the ends are tied down and they don't move, right? So in this picture, these pictures, I just have 4 different waves of the lowest energy that can fit in this box. Now, you can try number 15 by yourselves for practice. It's just one of those things to help you think about the problem. But let's think about these waves and their energies and their wavelengths. So we know a wavelength is one full sort of rotation of the wave. So this entire thing is one wavelength. And so if this length of this box is 1 meter, so let's write that this is 1 meter. Then this first wave will have a wavelength of 2 meters, right? Because this is just half the wave. The second wave here will have a wavelength of exactly 1 meter because the length of this box is just 1 meter. This third wave, this will have a wavelength of, it looks like 2/3 of a meter. And this fourth wave here will have a wavelength of exactly half of a meter, right? Because there's 2 waves in this box. And you can fit more and more waves in this box. All of these are possible, what we would call solutions for fitting waves into this box. And so if we were going to calculate the energy of these waves using the equation, the energy of, let's say, a photon is h over c times hc over lambda, hc over lambda, we will see that the energy is inversely proportional to the wavelength. So as the wavelength gets smaller, the energy goes up. So this here will have some energy, let's call it energy 1. This will have some energy, energy 2. This will have some energy, energy 3. And the energy will go up for each of these. Let's label these waves 1, 2, 3, 4. Because there's so many, we need to keep track of which one we're talking about. So I'm just going to put little labels on them, numbers. So if I were to plot the energy of these waves on a graph like this, where the y-axis is energy, the lowest energy here will be E1, the energy of the first wave, because it has the longest wavelength. The energy of the second wave, the energy of the third wave, they actually start to get closer and closer together as you go up and up and up. But here's an example of what I mean when we talked about their energy differences when we start to describe electrons as waves. There is no wave that we could fit in this box between this second wave and this first wave. So there is no energy that we can have that's between this first lowest energy and the second lowest energy. Similarly, there's no wave that fits between these 2 different waves. So that is, again, another example of quantization. Now, what I want you to pay attention to is the fact that there are many different answers to the question, what wave can fit in this box? And so to keep track of all the many different answers we could get, I put little labels like 1, 2, 3, 4 in them just to keep track of them. When we're trying to solve for the wave of an electron around an atom, for example, the equation that we'd use to try to find all the different solutions for waves of electrons would be this equation right here. It's a very short, simple equation called the Schrodinger equation. This is actually the time-independent Schrodinger equation if we want to get more technical. But this H guy is just called a Hamiltonian. This psi here, this is psi, psi, it's a Greek letter psi. right, represents the what we call the wave function. This is a function describing the wave of the electron, and this guy here, that's just the energy. And that's it. That's a Schrodinger equation. Solving that equation literally could tell you everything you would like to know about what electrons are doing in atoms and what molecules electrons are doing in molecules and how they come together, which, since atoms make up literally everything that we care about, or most everything that we care about, could tell us pretty much everything about the world around us. That is the Schrodinger equation. Now, when you try to solve this equation for the waves of electrons in the box of the atom, just like the waves in this box up here, you could have more than one wave, right? Like there's many different waves that could fit in this box. There's many different waves of electrons that could fit in the atom. So to keep track of all of them, the same way we labeled these with numbers, we need to give numbers to those different waves. And giving numbers to those different waves lead us to what we would call the quantum numbers, right? Because the electron waves are a little bit more complex than just the one-dimensional wave I just showed you. There are 4 of them. There's a principal quantum number, sometimes we call that n. There's the angular momentum quantum number, there's a magnetic quantum number, and then there's a spin quantum number. So 4 different numbers to label the different waves that we could get. The principal quantum number is, it's principal, it's the most important one, and its values are going to be, could be any integer, 1, 2, 3, 4, and so on, right? So n could be equal to 1, or n could be equal to 2, or n could be equal to 3, and doesn't really depend on anything else except everything else will depend on what that n value would be. So that's a principal quantum number. The angular momentum quantum number, so the principal quantum number is the most important one for determining what the energy of that wave of electron, what the energy of that electron is. The angular momentum quantum number, L, its values could be integers too, but it starts at 0. So it could be 0, 1, or 2, or 3, or anywhere up until n equals -1. It can't be higher than n minus 1. So what that means is if you have a wave with label n equals, let's say, 3, L could be 0, L could also be 1, L could also be 2, but L can't be 3 or 4 or 5 because the highest value for L would be n minus 1, which in this case 3 minus 1, that's 2. That's how we use the as angular momentum quantum number. So if you think about it, if you, for any n value, there are going to be n number of L values. I know that sounds weird, but if n is 1, then you can only have one L value, L equals 0. If n equals 2, there's going to be 2 different L values. N equals 3, there's going to be 3 possible L values, right? So the number n also tells you how many different L values you have. That's what this statement means. Okay, so that's the second quantum number, L. We're going to, because the principal quantum number is already using the same types of numbers, whole numbers, it can be confusing to use the same set of numbers to also talk about L. Because what if n is 1, L is 1? How are we going to, sorry, 0. Or let's do it, yeah, right? It's weird to label a wave like 1, 0 or n equals 1, L equals 0. It gets really confusing really quickly. So instead what we're going to do is we're going to give letters for these L values instead. That's going to make it easy. So for 0, L equals 0, we're going to call that S. For L equals 1, we're just going to call that P, right? Just to differentiate it from the n values above. So the letters are S, P, D, and F for L equals 0, 1, 2, and 3, respectively. Okay, and then after F, they just go with alphabetically G, H, I, and so on. So that's the first 2 quantum numbers. The third quantum number is the magnetic quantum number, ML, right? M subscript L. And these values depend on what the L value is, and they have values from -L all the way through 0 to positive L. So what does that mean? Well, let's say you have some wave right? Electron wave with n equals, let's say 2, which means L could be 0 or 1. Let's pick L equals 1. The ML value could be either -1, or it could be 0, or it could be +1, right? Anywhere from -L to +L. Those are different ML values. So what that means is, for any L value, there are 2L plus 1 ML values. So if L is 1, there's going to be 2L plus 1. So that's 2 by 1 plus 1. That's 3 different L values that we just calculated here. If L equals 2, ML could be -2, -1, 0, +1, or +2. Or if we use this formula, it's 2 times L value plus 1. So 2 times 2 plus 1. That gives us 5 different values. And here we have 1, 2, 3, 4, 5 different ML values. So those are the ML values. And then finally, there's a spin quantum number. This one's very easy to remember. There's only 2 possible values, +0.5 and -0.5. These are the only ones that are fractions. They're not integers, and it's +0.5 and -0.5. So those are the 4 different quantum numbers that come out of the equation, this equation, when you try to solve for the wave of an electron. And they all tell us something about what the electron is doing. And if we group electrons by their same number of n value, so principal quantum number n, we will call that a shell of electrons. So if we have 5 different electrons all sharing, let's say, the n equals 3 quantum number, then we say that these 5 electrons belong to the same shell, right? And shell is a good way to think of it. Think of it as like shells of electrons around the atom. So, for n equals 1 value, there's 1 shell of electrons. For n equals 2, let's use this color, there's another shell of electrons, and so on and so forth. That's a good way to think of it. If you have an n value and a specific L value, that's just going to be a subshell, right? So subshells are going to be stuff with a specific n value and a specific, let's say, L value. So if it's n equals 1 and L equals 0, we know L equals 0 is S, so we'll call this the 1S subshell. If n equals, I don't know, 3 and L equals 2, we know L equals 2 is the D label, so this will be the 3D subshell, right? So those are just how we label these shells and subshells. So shells will only have an n value, subshell will have an n value and an L value written as a letter. And if you have a combination of n, L, and ML all together, we have what we call an orbital, right? So those things create what we call an electron orbital. Has nothing necessarily to do with the Bohr model of the atom and the orbits that the electrons go around in there. Absolutely nothing. So if we think about the energies, just like how we have increasing energy here for increasing, numbers, right? We have increasing energy. These numbers that pop out of these equations here also correspond to different energies of the electron. And the lowest one is going to be the lowest n value and L value, right? So that's the 1s subshell. Higher than that, we have the 2s subshell, then the 2p subshell, then the 3s, then the 3p, and the 3d, and so on. And these different lines that you see are just the number of orbitals that we have. The 1s subshell, we have n equals 1, L equals 0 for s, and the ml value is just 0. So n, L, ml, there's only one combination there. There's only one orbital. Let's look at the 2s would be the same thing. Let's look at the 2p. The 2p, n is equal to 2, L is equal to, because it's p, L is equal to 1. ML could be -1, ML could be 0, or ML could be +1. And so there are 3 of them. So you have the combination of either n equals 2, L equals 1, ML equals -1. N equals 2, L equals 1, ML equals 0, or n equals 2, L equals 1, ML equals +1. 3 different possibilities, and so you have 3 different orbitals. They all have the same energy because the energy, for the most part, is just determined by the value of n and L, not so much ML. ml is a magnetic quantum number, so the energy for here, these values, will only change if you have a magnetic field. So if you put a magnetic field, these could shift in energy, but for the most part, they have the same energy. So that's why we have 3 orbitals in the 2p subshell. 3s will only have 1 orbital, 3p will have 2, 3d will have 5, and so on. Sorry, I said 3p will have 2. 3p will have 3 subshells, orbitals. So that's just the energy levels of orbitals. We'll get back to energy levels of orbitals in a second. I just wanted to show you how the different number of orbitals and shells and subshells correspond to the various quantum numbers and how we can find them. Okay, so this brings us to the Pauli exclusion principle. And some of you might have heard of the Pauli exclusion principle. All this states is that no 2 electrons can have the same set of 4 quantum numbers. We learned about how there are 4 quantum numbers. No 2 electrons in the atom can have the same set of 4 quantum numbers. So if the n value and the L value and the ML value are all the same, then the MS value must be different, right? That sort of thing. Okay, and then finally we know that the M, N, L, and ML values all make up an orbital, and inside of those orbitals there can only be 2 different MS values. So inside of every orbital there's going to be 2 electrons with different spins. Some people call that up spin and down spin, or positive spin and negative spin for the MS values. Alpha spin and beta spin, really, it doesn't matter what you call them. You can call them George and Mary, doesn't matter. But no 2 electrons can have the same set of 4 numbers. So one of the quantum numbers must be different from the other electrons in the atom. Okay, so with that, let's think about number 16. And if you want to pause the video here and try to figure it out, then go ahead and do so. But in this question, they say that we have the shell n equals 4, right? What are the various names for each of the subshells? So that's labels like 2s and 2p that we talked about. What are the labels for the various n equals 4 shell, various subshells of the n equals 4 shell? And then how many orbitals are in the n equals 4 shell? Pause the video now, see if you can figure it out on your own. Then you can unpause and we'll go over it together. Okay, let's figure this out. So if n equals 4, what are all the possible L values we could have? Well, we can have L equals 0, L equals 1, L equals 2, or L equals 3. So that those are all the different subshells. And the name for these subshells will just be 4s, because L equals 0 is s. This will be 4p, because L equals 1 is p. This is 4sp, this is d, and this is 4f. Right, so those are all the names of the different subshells. Let's figure out how many orbitals there are. Let's use blue. For L equals 0, the ML value can only be 0. So N, L, and ML together make up the subshell. So this is one orbital. So this is one orbital here. Let's see for this one. ML could be -1, 0, or +1, right? Because L is equal to 1. So this here will have 3 orbitals for the L equals 1, for the 4p subshell. For the 4d subshell, ML could be -2, -1, 0, +1, +2. So that's 1, 2, 3, 4, 5. This is 5 orbitals. And then for L equals 3, ML could be -3, -2, -1, 0, +1, +2, or +3. So that's 1, 2, 3, 4, 5, 6, 7, 7 orbitals. So the total number of orbitals in the 4 shell is 1 + 3 + 5 + 7. That's 1 + 3 is 4, + 5 is 9, + 7 is 16 orbitals in n equals 4 shell. That's how we do that one. Okay, try to do number 17 on your own. Number 17 is asking for all of the different quantum numbers, so that's N, L, ML, and MS, associated with the 5D orbital. The 5D orbitals. So in the 5D subshell, all of different labels for different orbitals, and then how many are they? So let's figure it out. So in 5D, N is 5, and L is SPD 0, 1, 2, N is 2. Right? Okay. So that means that the various ML values that we could have will be -2, -1, 0, +1, and +2. Right? So these are all the different ML values. And then for each of those, you can have an MS equals -0.5 or +0.5. So every single one of these will be a -0.5 or +0.5. Those are different options we can have for MS. -0.5, +0.5, MS is equal to -0.5 or +0.5. And here again, it's asking us to write all the possible combinations, so we have to. Okay, so if we're thinking about it, for how many orbitals exist, orbitals would be a combination of N, L, and ML. So we'll have 1, 2, 3, 4, 5 orbitals. But if you want to think about how many electrons we have, that's a combination of N, L, ML, and MS, right? A unique 4 different quantum numbers. So we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, which makes sense because every orbital fits 2 electrons each in each orbital with a different spin, MS of +0.5 and -0.5. I'm hoping this is all starting to make sense. The different quantum numbers are different ways to just keep track of the electrons, and no 2 electrons can have the same set of numbers, and there are rules to what values these various numbers can take on, the various quantum numbers. Okay, with that, try to answer number 18 on your own. Pause the video, and you can unpause, and then we'll go over it together. Okay, so number 18, they give us different combinations of quantum numbers. And they tell us that one set of combination is incorrect because it's not valid. Something is wrong about it. Let's figure it out. A says N equals 3, L equals 0, ML equals 0. That seems right. L is less than or equal to N minus 1, so that's okay. ML is between -L and +L, which is okay. So this is okay. 2 says N equals 2, L equals 1, ML equals -1. Let's see, L is less than or equal to N minus 1, so that's okay. And ML is between -L and +L, it's -1, so that's okay. C says N equals 1, L equals 0, ML equals 0. L again is less than N minus 1, less than or equal to N minus 1, so that's okay. ML is between -L and +L, so that's okay. So this is okay. So it probably means that this fourth one is incorrect, but let's see why. N is 4, L is 1, that seems okay. L is less than or equal to 3, so that's okay. ML is -2 though. Remember, ML could only be between -L and +L. -2 is not between -1 and +1, so this is why D cannot be a combination to describe an electron. Okay, that brings us to the end of this video. In the next video, we're just going to go over quickly what all of these different values mean for what the electron orbitals actually look like. I'll see you then.